So welcome to module 9 in the Pawsey Supercomputing user training series on running jobs. This is module 9 out of the 11 of the series. This one is slightly longer than the other modules, so we're going to have a little pause about the middle of it, just to take questions and take a deep breath before we get into the second half of the module as well. So this is quite an important module in the whole training series, as it covers the what and the how of actually setting up and submitting scripts for executing computational workflows on the compute node. So this is kind of the daily life of researchers making use of the Setonic supercomputer. So we're going to describe what a batch script is, what are its key components. We're going to see how to submit, monitor, and cancel jobs, how to open interactive job sessions, and examples of running parallel programs using the batch scripts. Watch out for these signs to the presentation. They highlight key callouts for the module. So let's get started with the first part of this module 9 of running jobs, which is about submitting and monitoring jobs. First of all, what is a batch script? This is another jargon term that I'm going to use quite often in this module. We used to call it job script. Now we're using batch script just because it sounds a bit more accurate as a term. So a batch script is a shell. It's a shell script that is set up and used to submit computational jobs to the scheduler. So the special feature of it is that aside containing typical shell commands and instructions to execute your programs, it also contains additional information on the compute resource requirements that the scheduler needs to be aware of to manage the actual execution. So the commands you execute are written in plain shell script language. In this module, we're going to take bash as an example shell script language. The computer requirements for the scheduler are expressed in terms of comments. So lines started with an hash at the beginning of the script. All of the comments for the scheduler have to start with a specific header, which is sbatch, which stands for scheduler batch. We're going to see quite a few directives or options that can be put on the side of these header comments. All of these options can also alternatively be provided as options to the sbatch command, which we're going to use soon. However, we have a best practice to share with you. For improved reproducibility of your computational workflows, we recommend to specify all of the resource requirements within the bash script instead of the command line. And that's because in that way, your requirements will be written down and recorded in the scripts, and will make it easier for you to know what you ran and to run it again if you need it, or to share it with collaborators and so on. So encapsulating all of the requirements in the script will improve reproducibility. So now let's get started with a demo on the terminal on Setonics about using sbatch and SQ with jobs. Just a note that at this stage, we're just going to see how to use the keys, learn commands to monitor jobs and then to submit them. We're not covering yet the contents of the scripts that will come later in this module. So let's go back to Setonics. Here I am in my Scratch directory. In a previous module, I had git cloned a repository of exercises from the Pawsey GitHub repo. So if you haven't done it yet, and if you want to follow the exercises of this module, please run this command now in your Scratch space, git clone, and this address. So I had done it in a previous module, so I'm just going to directly change directory into the Supercomputing user training directory, and inside here into the running jobs directory. And I'm going to use sbatch, followed by the name of the batch script called submitMonitor.sh to have a look at how to submit and monitor jobs. And we can use the command sq-me just to have a look at what I have submitted. And you see the job is still pending. And it's now running. So this job should take about 30 seconds. It's just a dummy set of commands I put in the script. So it shouldn't take long. And what I'm going to show you is that when the job is finished, the corresponding job line will disappear from this output. And we should be almost there. I'm just repeating the command to keep track. And now the job is gone. So it means the execution is completed. And if I now ls to get the content of the directory, I get this output file that was not there before, slurm dash the job id.out, and that's the output of that job. I'm gonna go back to that later. So I've just used the sbatch to submit the job in the form of a batch script, of a scripted workflow, and sq to monitor its execution. This is relevant to these trainings. I forgot to do it now, but the job was able to run as well because I was lucky the queue was not too long. There is one example of flag that can be useful to provide with this batch, which is a reservation flag. We use this, for instance, with trainings, just to make sure that we have nodes available for the training accounts. And let me show you how to use it, just for clarity. So I can resubmit the job again. Now this time I will use this additional flag, reservation equal to the reservation for today. This is just for a live user training session. It's not active normally. It's called course queue, and I can submit the job again. And now you could notice that it started straight away because there's a node that was reserved, which is node 1008, which was reserved specifically for this training. This is the only case where we kind of say, okay, you can specify that in the command line because it is not about reproducibility of the workflow. It's just about using a reservation that was provided for this specific session. I think I will forget to use it in the next examples, but it will be probably fine because the queue is not too long today on Cetonix anyway. So there is a third command, which is quite important, which we're going to use in the next exercise, which is scancel, which is used to cancel a job that you submitted before it reaches the end or before it even gets executed. It might happen sometime. You realize you did a mistake in the input and you don't want the job to run and waste your allocation for nothing. So you have the ability to cancel a job that is in the queue as cancel. This is just the output I showed you in the demo. And let's now go to an exercise. This is for you. There are two parts here. Of course, if you haven't git cloned the repo and you want to do it, just clone it now. And then there's a few points that I'm going to leave it to you. In a couple of minutes, I will go through them with you. So let's have a look together here. So the first part of the exercise is about having a look at the output of the previous job. And you can see that if you don't specify any specific option for the output file name, that it will default to slurm dash the job id.out. So in this output, as I said, this was just a dummy script I wrote. The key output was a repetition of the host name where the job executed. And you can see there was NID and then a number. This is a naming convention for the compute nodes on Cetonix. And in fact, if I also run the hostname command here on the login node, you can see that the naming convention for the login node is different. Here it is Cetonix -0 dash a number, as opposed to NID for the compute nodes. And so as we were, so we just commented a bit on just an example of a slurm job output file with its name. Let us now do the second part of the exercise, which is about submitting a job script called cancel.sh, which is in the same directory. And we can see that the job is queued. I want to have it started Well, okay, the job is now running. Let me run it for a few seconds. And then let us use the command scancel to cancel it. And the command scancel takes as an argument the job ID of the job. So scancel 199.427. The job is now in status CG, which means completing, and that's because I prompted the scheduler to terminate the job earlier, the scancel command. And now let's have a look at the output of this job. This was number 427. We see there's an error at the end. It says slurm step error, job ID cancelled at this time. And this is one example, the first example we're seeing today of a slurm output inside the slurm message written in the output of a slurm job. There's quite a few types. Some of them can be more frequent than others. So this one is what you get if you cancel a job before it finishes and you cancel it yourself. Let me now submit the script for the next exercise that we're going to do soon after this one. Because today I am in this live training session and I have a reservation, and you guys today in this live session also have the reservation, and I'm using it just to speed up the times and skip the waiting. For people that are gonna take this training offline later on YouTube, this option will not be available. You will not be able to use this reservation. Let's do it now. And why am I doing that? Okay, the job is running. So this is the part for the next exercise, and I encourage you to do the same if you wish. Give it a go and submit the time limit script with sbatch as well. In about a minute, we're going to review the output of the job together. Okay, let's have a look at what I submitted. Okay, it's still running. And it's now gone. So it was job ID 199.431. Let's have a look together at the output of it and see what we can find there. So here I didn't, as you noticed, I didn't cancel the job. I just let it run to completion. In fact, there's a list of outputs, but then at the end, there is another type of error. It says again, error, job canceled due to time limit. So what happened in the script is that I designed the script itself to last for more than the specified wall time. And so this is what you should not be doing in production, of course. You would like ideally to have the wall time to be slightly longer than the required runtime to avoid the job being killed by this scheduler. But this is what happens. So this is what you find in the output when the scheduler has to kill the job because it didn't finish within the specified wall time. So when you encounter this error in an output of the job, the meaning is that the script could not complete before the job hit the wall time specified to the scheduler. And we're going to see in the next part of this module how to specify these things. But this is the meaning of this output. And so to continue on this thread of common error messages that you can find in a job output, let me show another couple of them. So one that can happen is segmentation fault. This typically comes from a program error, typically invalid memory access or insufficient memory. And you will get in this case a double error. So the 4 RTL error with 6 seg-B. This is the segmentation fault that comes out of the program. And then what happens after the segmentation fault is that the cancel the job because of the failure. But this segmentation fault typically points to an error in the program rather than Slurm itself. And then there can be out of memory errors. There can be various types of messages in this case. This is just an example. And you get another Slurm step. The error OOM stands for out of memory. And in fact, it is specified here. Some of the processes may have been killed by out-of-memory handler. And the srun error, which comes again out of Slurm, is out of memory. So this points to the fact that probably the resource request did not provide enough memory for compared to what the program needed. So the overall message here is that when something goes wrong with a job, the first thing to check is the output file and look for clues there of what may have gone wrong. Look for error messages, look for warning messages, and try and understand from there what went wrong. Okay, a couple of more slides before a small pause in this module. So this one is just about some extra potentially useful Slurm commands that I'm not going to demo on the terminal, but just mentioning, and there is more information in the user documentation on the Pawsey website. So there is a command that allows to inspect detailed information for a job that is currently in the queue, either waiting or running, and it's scontrol. Gives information such as the resource request, starting and end time, work directory, even the path to the batch script that was used to submit the job, and so on. There is a command called sact, which stands for Slurm accounting, that provides the list with your history of previous jobs you submitted. And it comes with a handy list of options that can be used to tune the output to your needs. And again, more information is in the user docs. And the third one is SF, Slurm efficiency. You need to provide the job ID. So it's specific for a given job that finished, and it provides information on resource usage in a kind of human readable way, in a human readable format. Just for the record, this is an example of output for the second command I just commented on. So the accounting with the history of previous jobs. And then, yeah, so this is one more demo before we have this pause in the middle of the module. This is about interactive job sessions. So most of the time, it is recommended to submit your computational workflows as batch scripts, because that enables automation. That means that you can submit the job, go out for a coffee, go out for a run, and the scheduler will take care of executing the job for you. But there can be some cases where you need to actually run computationally intensive tasks interactively. So you are debugging your setup, you are testing things, or it is an inherently interactive program that you need to run. So Slurm is an option for that. And let's see that with a demo. So this is the command salloc, Slurm allocation. So this enables using opening an interactive allocation in the compute node. And let's see what this means. Before running salloc, let me just remind you that I'm currently on the Setonix login node, and I can see that with the hostname command. Let us now open as an interactive allocation with because I'm on a live session today. Let me use again the course queue reservation just to cut the time short. And let me just let us just go like that. And we get you see, I get the job granted, the allocation granted straight away thanks to the allocation. You see that I get the output saying that this node 108 is ready for the job. And in fact, I can tell, the way I can tell I'm now in a compute node is by using hostname. And now the hostname reveals that I'm running the command on the compute node, NID naming convention, not on the login node anymore. So remember, that's always the place where to run computational intensive tasks, even interactive ones in this way. Never do that on login nodes, not to overload them. So if you request, so sometimes your request will need to wait. It won't start straight away. This is a little spoiler from what I'm going to show in the second part of this module. So the salloc command can take all of the options that can be taken in the sbatch headers that are in the batch script and also in the sbatch command. And I'm going to use this capital N just to request a large number of nodes that I know are not available right now. And when the resources are not available, what you will get as an output is pending job allocation. So the job is queued and waiting for resources to become available. And that's what you get in terms of output. When the resources become available, you will get an output similar to the one above. So granted job allocation, and you will be able to use the interactive shell on the compute node. Okay, let me kill this request with Control-C and go back here. And this is what I just showed you. Okay, we're now halfway, more or less halfway through this module 9 on running jobs. Before moving on to the second part on actually the contents of the batch scripts, I'm happy to take any questions. So let me move on. We're still in module 9 on running jobs of this Pawsey supercomputing user training series. And I'm going to start now with the second part of this module, which is about writing batch scripts. So we've seen how to submit and monitor them in the first part of the module. Now we're going to see the contents and how to specify resource requests to the scheduler using the requested syntax. Before entering these details of how to write a batch script, we're going to see examples of parallel programs as well. And so let me just take a couple of slides to talk a bit about some common programming models that are used in programs that run on supercomputers. And to do that, allow me to just provide a couple of definitions. So what is a process in computing? So a process is just a running instance of a program, which comes with its own private space in the memory, in the RAM of the hardware where it's running. And also, yeah, it can be executed as one or many threads. We're going to see what that means quite soon. Let me just focus on this process a bit more. So imagine on your desktop, you might have Microsoft Word. So Microsoft Word is a program. It can be run in multiple instances. So imagine you have to edit 2 documents at once. You will need to open 2 windows of the Word program. Each one of those 2 windows are 2 running instances of Word. And so effectively, under each one of those instances, there will be a process running. So that will mean that you have 2 word processes running at once on your machine. And that's the same in the context of supercomputing. You can have the same program running over multiple instances, so with multiple processes. And why am I saying that? Oh, wait, I'm going to say that in a minute. I also mentioned that a program can be executed as one or many threads. So what's a thread in computing? Within a single process, within a single instance of a program, a thread is the smallest sequence of instructions that the program needs to run. And so again, you can imagine when you type on a Word program, you may have instructions to say, actually add text to a paragraph, instructions to set up the layout and formatting of the page. And you can imagine that those instructions, some of them can be executed independently. So they represent independent sequences of instructions. And those are also called threads. Why am I saying that to you? So, well, one of the most common programming models for high-performance computing is distributed memory parallelism. And this paradigm makes use of multiple processes of the same program that execute at once to divide and conquer a large computational workflow. And for instance, it's called distributed memory because these processes can actually run on distinct compute nodes, so on distinct pieces of hardware. And whenever they need to communicate, to exchange information, they will do that via so-called messages, which travel through the interconnect network that connects the nodes together. So we've talked about the interconnect in module 1 of this training series. The most common specification for distributed memory parallelism is called MPI, which stands for Message Passing Interface. And we're going to see an example of how to set up an MPI batch script later in this module. Another quite common paradigm is shared memory parallelism. In this paradigm, a single process, a given process, is set up in a way that just the more computationally intensive portions of the program are able to execute via multiple threads at the same time. So it means that the program is able to take bits of instructions that can be executed in parallel because they don't depend on each other, and they will execute in parallel via so-called threads. Notably, because these threads are part of the very same process, they share the same space in memory, and then they share the same portion of data or information. That's why it's called shared memory parallelism. A very common specification for this paradigm is OpenMP. We're going to see examples of setting up a shared memory batch script later in the module. The third and last programming model I'm talking about right now is GPU-accelerated parallelism. This is a paradigm where which takes an heterogeneous, that is multi-device approach, where the program will still be started on a CPU, on a central processing unit, which is what we have right now on the phase 1 nodes of Setonix. But then the program will offload the most computational intensive portions to a dedicated piece of hardware called GPU, which comes originally from graphics processing unit, from the video gaming world back in the days, but it's now being used for computational intensive sciences as well. So a GPU is a specialized hardware that is designed to process large blocks of data in parallel. It's very good for offloading those very computational intensive parts of a program. There are various programming interfaces available to write programs that use GPUs. There is HIP by AMD, which will become very relevant for phase 2 of Setonix late next year in 2023. CUDA by NVIDIA, OpenMP for target offloading, and others here in the list. We're just going to have a very small example of this later in this module. Okay, with that being said, let's have a look at what a learned batch script looks like. And let's just start by one of the previous scripts we submitted with sbatch in this module. So here I'm just pretending I am on the terminal, and I am printing out the content of this submit monitor script. So let's have a look. So the first line, it's called the shebang line. It's a shell definition. It declares that the script is written in bash and needs to use the bash interpreter to run. We recommend to always use the -l or --login option for bash to ensure that that bash fully configures the shell environment for the job. So provides all of the environment configurations needed to run properly on the compute node. Then the second block in orange is the main topic of this module. So I'm gonna talk about that very soon. Let me just quickly mention the third block in yellow. So this is the part where you as the user will write down the commands you want to execute. So this is the part that is written in the shell language, in this case bash. So it can contain commands, any legal bash syntax. So any commands to configure the software environments, for instance. So configuring software modules that I talked about in user training module 5, or configuring software containers we talked about in training module 6. But you can also define variables, manipulate files and directories, post-processing tasks, and of course execute the applications. So everything that is in here is kind of specific to your application, and may require some knowledge of the bash shell scripting language, which is outside the scope of this module. What we're going to focus on right now is the orange block, the one about the scheduler configurations. As I mentioned at the very beginning of the module, these configurations in the script, in the batch script, takes the form of command lines that start with #sbatch. And let's now talk about the most common options that can be specified with this syntax. So the first one here in this example is the job name, which is optional. It's used to assign a meaningful name that you want to assign to the job. Just to better identify it, for instance, in the queue, in the output of the queue monitoring command. By default, it will just take as a value the file name of the batch script itself. Another optional specification is account, which needs to take the value of a Pawsey project, of your project ID for your allocation. You don't need to specify it unless you are a user that belongs and is a member of multiple projects. In that case, you may You may need to run some jobs with a project, some other jobs with another project, and then you need to specify the project ID with the account option. Another option here is the partition option. This is quite important. So this is to specify the scheduler partition. We talked about Slurm partitions in the module 8 of this training series, job scheduling overview. The default partition, if you specify nothing, will be the work partition, but there are other ones that can be used depending on the needs of the specific job. Another option is the wall time, the maximum duration that you want to ask for the job. The default is 1 hour. Each partition has a maximum value that can take in here. So for the work partition, it's 24 hours or 1 day. Other partitions may have different maximum values. This will tells them how long, up to how long the job can run for. And another option that I'm going to comment on here, which is not shown in this example, is the QoS option. This stands for quality of service. This is another feature of the scheduler that we covered in training module number 8 on job scheduling. The default value is normal, but if you need for instance, a high QoS, you can specify it with this option here. Let us now discuss a bit those options that refer to the size of your job request, so to the number of cores and nodes, CPU cores and nodes that you need for your job. And here we're going to refer to those definitions of processes and threads that relate to the MPI and OpenMP programming models that start with the MPI case. So many processes that you need to run for your application to run at scale on a supercomputer. So one key option here for them is ntasks, which actually maps to the number of parallel processes for your MPI job. And then when you basically the scheduler will look for as many cores. We'll need to allocate as many cores as the number of tasks that you requested. Another specification that you need for the number of tasks is number of tasks per node. So the two of them together will enable the scheduler to know how many CPU cores per node and how many nodes to use in total. So say you are asking for 256 tasks in total and 128 tasks per node, it means that the scheduler will need to allocate 2 nodes in total, each one with 128. So the two together will make sure that the scheduler is able to allocate the resources that you need. An alternative, there is another way of seeing this. Instead of specifying n tasks per node and n tasks, you can specify n tasks, which is the total 1, and then the number of nodes instead of n tasks per node. It's good to pick a combination of one of these two to enable them not to spread your job request over too many nodes, but instead keep your request as compact as possible. Use the minimum number of nodes possible, pack your task in the minimum number possible of nodes, which will result in a more efficient running for both you and the other users. And note that the default for this configuration is always 1. So one task per node, 1 node. And finally, there is also the CPUs per task option. This actually maps to the number of threads per process, which we talked about for OpenMP programs. And again, the default is 1. If you are using an OpenMP job with, say, 1 task and 8 CPUs per task, it means that the scheduler will need to allocate 8 CPUs in total. Now, there is a very important, there's an important aspect to remember. We know that compute nodes in the work partition and most compute partitions on Cetonix have 128 cores per node. This implies that for Cetonix, n tasks per node times CPUs per task must be smaller than or equal to 128. Okay. This is to reflect the actual hardware capabilities of the class, of the supercomputer. And finally, we have also one last option about hardware resource request, the MEN option, which is optional. You don't always need that one, which allows you to specify the total memory per node which is required. By default, Slurm will take a proportion of the requested n task times CPUs per task, make the proportion to 128, which is the total, of course, and multiply it by the total available RAM, which is 230 gigs. And we'll take that as the required memory. If you need more than that, you can use this mem option to request for more, with the limit, of course, of 230 gigs in the standard word partition. Okay, now let's talk about options relating to the access mode for the node. So in the module 7 on the accounting model and computer allocation, we mentioned that compute nodes on Cetonix can be either used as a whole, or but a fractionary use of a node is also allowed. And so this is what shared node access is about. So this is the default mode. It is useful if the program cannot scale to use the entire node, to use all of the 128 cores of the node. In this case, the allocation is just charged for the partial node usage, taking a proportion, as we mentioned in module 7. This also implies that other jobs can run on the same node at the same time, which means that the performance may be slightly less predictable. And it's also worth noting that as we speak right now, the pinning of processes and threads to the actual hardware is not optimal. It will be fixed in future updates of the software environment on Cetonix. When shared node access is selected, so when you are using less than 128 cores per node, we recommend to use a couple of options to make sure that the tasks and threads requested stay as compact as possible. They're not spread over multiple nodes. They all run within the same node if possible, if available. So one option is distribution block to enforce this stacking. And if you're using less than one socket of a node, which means in practice less than 64 cores, you should also define n tasks per socket to make sure that the resources stay packed within the same socket. You might remember from if you've watched module 1 on this series, that each compute node on Cetonix is made up of 2 sockets. So each socket has got 64 cores. Just a note, if you can, try to use, when you select multiple processes and threads to run your applications, try to use multiples of 8, your processes and threads in multiples of 8. So again, as we saw in module 1, 8 cores within a node share the same cache memory. And so by selecting multiples of 8, we optimize cache utilization, both by your job and by other people's jobs within Cetonix. So the other option to shared access is exclusive access, which means that you're going to use the entirety of the node. This is useful in a few cases. So programs that are able to scale up to one node or even to multiple nodes. Programs that maybe do not scale to the whole node, but need the entire memory of the node. And this can also be useful if you want to run benchmarks, if you want to measure the performance of your run. For instance, if you are collecting figures for the meta allocation call or for your own usage. In that case, you want predictable performance. So you want the entire node to be allocated just for your job. And that's what you get when you're in exclusive mode. All of the cores and memory are for you. The performance are more predictable. Of course, you get charged in terms of allocation for the full usage of the node. And in this case, also the process and thread pinning is fully supported at the hardware and software level. To use to enable exclusive node, which is not the default, you need to add the exclusive flag in the batch script. Okay, so these were the key options I wanted to discuss with you. Now let me share a couple of tips for batch script. The first one is about reproducibility of the script. So we recommend to be explicit and do not rely on defaults for the key resource requirements, even if these defaults exist. And in particular, we recommend to always specify at least the following. So the partition you're running on that actually imply maximum core count and maximum memory. So this is important for reproducibility. Specify n tasks per node, or nodes, one of the two. CPUs per task, and time. So always be explicit at least for these, and do not rely on default for better reproducibility. And also another tip, which we're going to cover a bit in more detail in the next module, module 10. The first time you set up a new batch script, it's very good to perform test run, which can actually just be, okay, you submit the job and you monitor it when it starts to make sure that it works, that what you requested in terms of resources is correct, that your setup of the batch script is correct, and that the outputs that you are getting are what you were expecting to get in terms of the setup. Of course, if you need to perform these tests in a prompt way, you may want to just set up a little trial run to make sure it doesn't sit for a long time in the queue. You can perform this test promptly. Okay, this was all about the setup of the resource request. There is one more bit that I need to discuss with you about the contents of the batch scripts in general terms, and it is srun. So srun is a tool provided by the scheduler that ensures that the program is using the assigned compute resources at best. So optimal pinning of processes and threads to the cores and optimal usage of the actual resource assigned. If you don't provide any options to srun, it will just use the resources that are defined using the sbatch directives up in the script. Well, sorry, I didn't mention how to use srun. So, well, when you're executing your program in the batch script, so here in the second part of the script where you're putting the bash commands, you should prepend the actual execution of the program name with srun. So it will be srun in the program name and any options. So this is the case one of usage with no extra flags. We'll just use the provided resources in the sbatch directives. If there's a part of your workflow in the script that just uses a subset of the requested resources, you can specify a subset of resources in terms of flags just for that srun execution. In this case, it's a good practice to use --exact to make sure that srun is actually using just that subset of resources. And then you can use the very same flags and tasks, CPUs per task, and so on. There are shortcuts available if you want to type less. -n for task, -C for CPUs per task, and -N for nodes. So this is what you need to prepend to your programs when executing in a batch script. Note that srun is strictly needed for running MPI applications to spawn multiple processes. It is not strictly needed for serial and multi-threaded programs. However, it is a good habit to use it for those programs as well, just to form the good habit to always use it. Okay, so now I'm just going to go through a couple of practical examples with some numbers of resource requests to give you an idea of what you may want to use depending on the type of program. So the first example is an MPI program, which then needs to run multiple processes with exclusive node access. So what we have here is an example where the program needs, let's look here, 256 tasks and 128 tasks per node. It means that it will run over 2 nodes of Setonix in total. This is a division between the 2 values. And in exclusive mode, so exclusive node access, because it's using full nodes. Here in this picture, and also in the following slides, I'm just representing a single node. So in this case, one of the 2 nodes being requested by the job. And we're requesting 128 tasks per node. It means that here, so we have these little rectangles, light blue teal rectangles, which represent 1 core each. And on each one of these cores, there will be a distinct process running. And in total, we have 128 for each one of the nodes. We now have an example of an OpenMP multi-threaded job with exclusive access. So in this case, it's just one task in total, 1 task per node, but 128 CPUs per task, which is what we use to be able to run multiple threads for the program. And so here, this is the whole node. There is just 1 process running in yellow, but then the process will spawn 128 threads And in fact, we can see 1T associated to each one of the cores in the node. Also note that when running specifically OpenMP multi-threaded jobs, there are some additional variables that is a good practice to specify to make sure optimal runtime of the OpenMP program. So it's good to specify OMP num threads equal to this Zerm variable, Zerm CPUs per task, which will equal the requested CPUs per task here. And this will enable the threads to this will enable the program to run 128 threads in this example. OMP places, this is a bit technical. Let me just say that most of the time, setting it to cores is a good idea. And then OMP proc bind, this tells OpenMP how to spread the threads over the node. This is most important if you are running an OpenMP job that doesn't take a whole node, but just a fraction of it. So you have two typical options, close and spread. When you select close, the threads will all be packed together in the same part of the node. And this is good for improved cache and memory sharing between the threads. Whereas if your programs is memory bound, it needs a lot of bandwidth of memory to communicate between the cores and the RAM. It's a good idea to spread the threads over the node to maximize the bandwidth of cache and memory between cores and memory banks. This is a bit technical. I'm not going into further detail at this stage. We also have here one example of one hybrid application, which is able to exploit both MPI and OpenMP parallelism at the same time. In this case, we're asking for 4 tasks and 2 tasks per node, but then each of the tasks is able to spawn 64 threads, and therefore we are requesting 64 CPUs per task. And again, we see it depicted here just for one node out of the 2 total ones that are required. And you can see in each node, there are just two processes being spawned corresponding to the 2 tasks per node here. But then each process will spawn 64 threads, which maps to 64 CPUs per task here. Let me now have a look with you at an example of MPI with shared access. So it means that we're not using the full node. In this example, we're just running 64 tasks and then 64 tasks per node. As I mentioned in a previous slide, because I'm using less than a socket, actually one full socket, it's a good idea to also specify n tasks per socket 64 to make sure that the selected cores are all in the same socket for better performance. And then also using distribution block for a similar purpose. This is mostly useful if you are using less than a socket. And this is the outline. So 64 MPI processes all running back together in the same socket with shared access. So it means that this job will only be charged for half of the node usage. And one of the last examples, a shared access with a memory request. So in this case, it's actually a serial job. So one task per node, 1 task per socket, 1 CPUs per task. So serial job just needing 1 core to run, but we're requesting 58 gigs of RAM, which amounts to 1/4 of the total RAM inside a node on Sotonix. And so here you see that the allocated resources, so there is just 1 process or thread running, but we're still getting 1/4, 1/4 of all of the cores are located. And that's because we're requesting 1/4 of the RAM. So in this case, the allocation will have to be for 1/4 of the node. And the very last example, requesting a GPU. So this example currently applies to a couple of our legacy supercomputers, Topaz and Garawala, and it will apply to Sotonix Phase 2 when it gets deployed in the future. So here I'm just mentioning to you that there is a specific option to request GPUs, which is GRS equal GPU : and the numbers of GPUs per node you need. This is what you would request if you need to run a program on a GPU. As I said, applies to Topaz, Garawala, and the future deployment of GPUs on Sotonix.
Okay, so I've talked a lot in this second part of this module. Now it's time for a small exercise. So we can go again back on the downloaded repositories with examples on your Scratch space. There is a subdirectory examples inside the running jobs directory. And here, basically, we provided you with the very same scripts that for which I've discussed examples with the various MPI and OpenMP settings. I'm providing them with a program that just does perform a very simple task. So in this exercise, have a look at the content of the directory, pick one job, one batch script, and submit it to the queue with a sbatch. And then we can have a look at the output together. What I'm going to do now myself, I'm going to pick the hybrid one, the hybrid MPI OpenMP example. See, there is a list of available scripts. And yeah, probably going to wait a minute or two, let you go for it. Okay, here are the instructions. I let you go for that, and then I'll comment on what we can do along the exercise. Okay, so let's give it a go together. So the first step in this exercise is just to run the make command. It's because there is a source file for this for the hello program that needs to be compiled. And that's it. We now have this hello executable, which is used in the scripts. Let me just have a look at the available resources right now. Yeah, okay. So I'm going to run the hybrid example with a little modification. So I wanted to write the example exactly the same as in the slides. So this example here requires 4 tasks and 2 tasks per node. But written in this way, I cannot run it with the reservation that is available for this live training session. So this is something that if you're doing it yourself for your own self-study, you probably don't need to do that. Let me just change these end tasks to 2. In this way, I will be able to submit the job with the reservation, which is just for 1 node. That way we can hopefully get the output in a faster way without waiting on the queue. And the runtime is quite small as well. So let's have a look at it. It will be job hybrid.sh.out. Let me reduce the size of the output for a moment. Okay, basically what this program does, it just prints an hello word from each CPU, basically, that was requested by the job. It prints the host name of the process, and then it tells you the rank means the process ID. So I was asking 2 processes. This is first output is rank 0, and then the second part is rank 1. And then for each process, it gives the thread ID out of the total threads. And you might remember from the slide of this hybrid example that we were indeed asking for a number of processes and 64 threads per process. And this simple hello program just displays that information for you in the output, just as a silly dummy example for this training. One little note, just to give you the idea that there are many more options that we couldn't cover in this module, and you can find information about that both on the Pawsey documentation and on the Slurm documentation. You might have noticed that the output of this job was the job script.out instead of the default Slurm job ID. And the way I achieved that was by specifying yet another legal sbatch options, which is output, to provide the name of the output file. And within that, I actually use this wildcard that is available
in the directives, this %x, which actually gets substituted at execution with the name of the job script, the name of the job, which in this case defaults to name of the job script. So this is just, I don't want to confuse you. This is just to give you an idea that there are many more options out there available to customize your batch script with them, and you can find more about that in the documentation. And this is just the output I showed you. This was quite a long module overall about running jobs. We learned about what is a batch script, what are a process and thread in computing. We learned how to use sbatch, skew, cancel to monitor and submit jobs, lock for interactive sessions, and then we covered extensively the syntax. These are the basics of the syntax of batch scripts with a few examples. And finally, we covered some best practices about setting up and running job scripts or batch scripts. On the Pawsey support portal, there is extensive documentation that covers in detail a lot of areas. And we also have a support portal in case you have issues that you can't solve by yourself and you need assistance from us, the Pawsey staff. If you want to stay updated with news and updates from Pawsey, you can sign up for the Pawsey Friend newsletter. So the module is finished, and the session is open for questions. And congratulations, this was the longest module for this series. So if you're still with me, well done. So yeah, I'm happy to take any questions before we move on to the next module, which is much, much smaller than this one.